Welcome to the fourth lecture, I guess. Chautha, yeah?
Yes.
Yeah. Okay. On probability and related concepts for random processes, right? So our goal is, of course, random processes, their properties, their modeling, and all that. But we cannot get there without going through the foundations of probability. So we have been doing that, and the last few things we did in the last lecture. क्या किया हमने last lecture में?
Device conditional probability
Hmm.
and total probability Bayes theorem
Right.
that we discussed last time.
So we were still working with probabilities,
Law of
right?
probability, like.
So when they are, we looked at the situation when they are, let's say the probabilities are equal or turn out to be same, either just by the way we define the experiment, we say okay they are chosen randomly with equal probability, we just claim it, or we calculate the probabilities of certain events and they turn out to be equal, right? So in that case the events were what? Equally likely. So everything we were doing was we were talking about probabilities, right? When probabilities happen to be equal for some events, then those events are equally likely. If it's the same for all events in the sample space, then they are all equally likely. Yeah. Then we also looked at kind of a complementary probability. If one event has occurred, then the other cannot occur, right? And those kind of events were, what were they? Mutually exclusive, right? So they were events that were equally likely, there were events that were mutually exclusive, and each of these has relation to probability. Yeah, here the probabilities of those events are equal. Here the two happening at the same time are impossible. Yeah, like probability of A intersection A complement, meaning A happens and not A happens, is not possible. Yeah, so mutually exclusive. Then as you mentioned, we looked at the Bayes theorem thing, which was what? So you had some probability on this variable, sorry, this event A, we haven't gone to variables yet, event A, and you wanted to update this probability with a new information. Yes, new information has arrived and you want to update this probability. So we found that there was Bayes theorem which was going to help us in that. Yeah, this is we do the mathematical juggling and we get here, but in essence this is what's happening. You had some, what was this called? Prior probability. Yes, and what did we call the other one? Posterior. Prior, before the fact that B happened, or you got knowledge of that. Posterior, after the fact that B happened, or you got knowledge of that. Yeah. So this was again related to probabilities. Yeah. Last one, as you already said, was the total one. Yes. Total probability is basically, as I showed you last time with the example of playing matches, you just put all the mutually exclusive possibilities and sum them up, yeah, and that turns out to be total probability. And we said the probability of B happening equals probability of B given AK, right? The summation over K and probability of A K. What were the conditions? Essentially this is what you know from formulas. This is probability of A, B and AK, right? What were the conditions on these A's? This is not true in general. Okay, the A's have to meet some conditions for this total probability to hold. What were the conditions?
Probability of greater than or equal to
So A's should span the
span, yes.
sample space. So the union of all A's should be omega. Why is that required? Otherwise you have missed some possibility, right? Then you will not get the total probability because you have skipped some probability. Was there any other condition on that?
Discuss some dependency and
A's had to be mutually exclusive. AK's are mutually exclusive. So they have to be mutually exclusive and together they must span. So in a way we are saying AK's must be all the simple events inside omega. Simple was which were mutually exclusive and they all together made omega. Remember? So that's what we are saying. Why is that required? So you're doing a summation. Remember? Summation is only possible if there is mutual exclusive. If it's not there, you always have to subtract something. This becomes more complicated. You can still solve and try to put more terms here. Yeah, but it becomes very complicated. In its very basic form, total probability is this. Why do these come in handy? Why do we need this? As I said, also from the example of, we'll see more examples maybe later, but since it's not course in probability, I don't want to spend too much time. But really, this thing has its roots. Even this thing has its roots in the real situation. As I said, in real situation, we often know the conditional probabilities. My chances of winning a chess match, I don't know. Yeah. Now, my chances of winning a chess match if I'm playing a 3-year-old. High ho gaye? Yeah. My chances of winning a chess match if I'm playing Kaspersky, the guy, well known chess master. Kya ho gaya? Almost zero. Yeah. So we often in real life and data based, when we make data, we often have conditionals. Okay. We often have conditionals. Sometimes we may have a prior guess. Okay. But otherwise it's not really available. So in its basic form they are often hard to find, so we try to find them based on what is available and then we refine them. Maybe after that I now know that an event D happened, let's say. Yeah. So then what is the probability? I could use that to now further update it. Yes. So conditionals are the formulas are nice, but in my experience and knowledge, the importance of all these formulas also stems from the fact that most often in real applications, real problems, it's the conditional information that we have available, and then we need to either change the condition, reverse the condition, or we need to get a total effect of all the conditions. Yeah. Probability that I play this team and win, probability that I play that team and win, probability that I play team C and win, given that there are only 3 teams. There are only 3 teams means this is covered, and that I can only play one of them, mutually exclusive. Yeah. Then you can get the total chances of my winning. We did that in detail last time, so I just skipped that. But this sums up all that we did in the whole lecture. Yeah, we took 1 hour for this. Because why? We developed each one. We started with some generic question, thought, or a problem, and that led us to these formulas. Yeah, so that's why it takes a bit while. But then usually once you have gone through that development, it is good to summarize in your mind, in your notes, everywhere, to summarize what really you have done. Okay, so today we are going to the next step, from basic probability to its actual use in where we want to get to, random processes. Yeah, so we have been talking about probability being lack of knowledge, the lack of knowledge coming from many reasons. Yes, so exactly, and we realizing that okay, all these reasons can add what? Uncertainties. Yes. So from now on, I will talk about, instead of saying lack of knowledge, which doesn't sound very nice, it seems we jahil hai shayad, yeah, we will say uncertainties. Reasons we know now, yeah, kai causes, there are many causes, but from here on we'll start calling them uncertainties. So we realize that there are situations where we have to deal with uncertainties, yeah. So why not embrace the uncertainty, accept the uncertainty, and make it part of our calculation? Now this goes quite against the spirit of old mathematics, which wants to be precise. ऐसे ही है ना,
Yes.
मतलब एक एक डेसिमल तक जो है वो infinity का भी जो निकालना है, you want to be precise. But now for the first time in probability theory, we go away from that. Yeah, we say okay, reality doesn't care. Math says your face looks like this, but it looks very different in throughout the day. When you wake up, when you're sick, right? So when you're happy, when you're sad, it varies. There are variations, there are uncertainties because of those variations. So why not embrace those uncertainties, accept them? Yeah. So today what we will do is this: we will one by one add this prefix पता है वो जो पहले लगा देते हैं किसी जुमले से love से. So we'll add this prefix of random. So you know what is an event, yeah, you know what's a variable, you know what's a process. So today's goal is to embrace since it's gonna be there in real systems, in real applications, so we need to embrace this uncertainty, and in embracing it we will go okay, what we know so far or what we've been working with often was deterministic. Opposite of random is
Deterministic.
okay, so just term use karte rahiye. Yeah, so there was deterministic event, we will put the prefix random with that. Okay, so we will go to random event. Okay, you have familiarity with deterministic variable ever since you first learned algebra. किस क्लास में पढ़ा था, अब तो याद भी नहीं आ रहा. When was it? Not algebra, I mean when did you first learn algebra?
7 by 6 7 में सिखा देते हैं basic.
A B X you start seeing. You have been seeing deterministic variable. Yeah. Now we will go to the variable being random. Then you have been seeing in some cases processes. Okay. Relation of, let's say, acceleration and velocity. Rate of change of velocity is acceleration. It's a process of change. Yes?
Yes.
Velocity is changing. So you had the fixed formulas, koi, but now random processes. So what we will do is we will start with the deterministic and we will bring our uncertainty in there and we will start to establish the let's say foundations of going into randomness. Okay, taking our maths towards a bit of uncertainty, right?
So, what are the reasons that we're going to random process? Is it mean that our deterministic model are restricted in some domain?
Yeah,
That's
yeah.
why we're approaching to random.
Yes, yes. As I said, the uncertainties are there, right? So as long as uncertainties are there, deterministic will fail in many real applications. Yeah, because of that, it's very and from Einstein's example of using deterministic or sorry stochastic modeling to find this motion of the pollen grain, right? Calculating the exact motions of all atoms is extremely hard and you wouldn't know mostly what's the initial condition where things are starting. So we have discussed that either it is too hard to do, to give the exact deterministic thing, or it is because there are so many variations are possible that or the event hasn't happened yet and you want to guess about it in the future, right? In that case you need to go for deterministic random processes. You have to bring in uncertainty, and then you have to work with the uncertainty. We're not just saying that we'll make it uncertain and then say, yeah, okay, it's uncertain, let's leave it. Yeah, we have to design something, some solution that works within the uncertainty. It doesn't fail. Okay, I give the example of the door every time. It's because it's a simple example. The example of the picture, your face. Uh, we need to allow changes in there. Okay, your mobile for the first time takes one picture of your face. Yes, even the fingerprint mobile. You know, sometimes we have small cuts here or something. Yeah, so skin is dry sometimes. Even with the fingerprint, if you say no, whatever it took for the first time, takes 3 samples usually at first time. Yeah, so it matches. If your fingerprint next time matches one of those 3 samples exactly, I'll unlock it. Otherwise, it's over. Yeah, you cannot use it. So चलेगा फिर बहुत मुश्किल हो जाएगा. It will be believe me, it will be very hard. That is what has led to a lot of stochastic modeling, data series analysis, and those have led to these neural networks and all those things. Okay, they are also trying to work with variations. Yeah, so reality. A short answer is that all the mathematics you have learned is nice and all, okay, but reality is not that deterministic. Simply, okay. Um, and there are many examples. Try training a car. आपको you are a driver, you can see, okay, this is a person, this is a bicycle. गाड़ी को train, smart cars, they are self-driving cars. It's a headache. Why? If the world would be so deterministic, why not just put some formulas in there and car will tell this is a bicycle, this is a truck. What's wrong? One of the I remember somebody was showing one of the Tesla cars was identifying. So there was a lorry in front of it, a truck, and on the back of the truck there is a big poster of a cycle. So the Tesla car was trying to slow down, thinking that there is a cycle in front of it. Right now there is a cycle. There is a huge picture of a cycle, which is actual real size, but it's a picture on a truck, right? So we can decide, yeah. But if you don't build in uncertainties in the system, आप पागल हो जाएंगे. उसमें कितने डालेंगे system? How many options will you train or put into the computer? ये भी हो सकता है, ये भी हो सकता है. Deterministic would require you to put all the possibilities in there. Why not assign probabilities to them? Most cases this is how a bicycle looks. In some cases this is how it will look. Yeah, assign it a distribution and then work with the distribution. Yeah, so design so that 99% of the time, 99.9% of the time it is fine. Yeah, so like that. Otherwise it will just be processing. Let's say I could take a million pictures of your face during many days. Yeah, and I don't want to have a random model in my mobile. Now you show your face, it's going to unlock from the front or back, and your mobile is now comparing your photo to those million pictures so that it can match one of them. Yeah, it doesn't miss any of your variations. It will not unlock million के साथ compare करने पता कितना time लेगा. उसके बाद फिर कहीं आपका कट शट लग गया छोटा सा तो वो फिर माइनस हो जाएगा. After million you're still not able to unlock. So sometimes bringing in the deterministic variations, all of them, bringing them in also means that there is a huge computational cost. Time बहुत लगेगा. Yeah. So again that leads us to designing probabilistic models. अब उसमें खराबी क्या है? Yes, there can be situations where someone who looks very similar to you may be able to unlock this mobile, because what we design allows variation. Variation means to some extent variation. If there is someone else whose face looks a lot like you with a very small variation, then that system will allow it. Right? Do you think so? There are, of course, there are um, let's say cons or disadvantages of going this way, but we can always plan the disadvantages. We can say, okay, this test is 99.9% accurate. Okay, we can try to do that. Or we can say, okay, if you take the COVID test once, the possibility of correct result is 80%. But if you take it twice and you get the same result, the possibility goes to 95%. Yeah, कभी होता है double test भी लेते हैं. Why do we do that? Who calculated it? किसने बताया? All of that comes from this mathematics. Yeah. So short answer, yes, reality is not very nice. So let's start with deterministic event. Can you mention some event? Event तो होता है something happening. Yeah. So कोई आती है ज़हन में कोई भी event, let's say.
कॉइन टॉस करने का हेड स्टेल
वो random होगी ना, right? Okay, that's one event, and it is random. We have discussed why it is random. Or any other event.
Sunrise from the east.
Sun rising from the east, right? Is that a deterministic event or
Deterministic.
random event? It is deterministic event, right? At least till क़यामत तक, तब फिर एकदम उल्टी हो जाएगी. Yeah. Okay. So I've written moon passing between earth and sun, right? क्या होता है इससे जब it passes between earth and sun?
Rise होता है.
No, no, वो
ग्रहण होता है
हाँ, किसका होता है? सूरज का होता है, चांद का होता है?
Moon.
Moon
Moon
passing
ग्रहण.
between earth and sun.
चांद ग्रहण होता है ना
नहीं,
सूरज ग्रहण होगा क्योंकि
सूरज
उसकी
ग्रहण.
रोशनी नहीं पहुंच रही जमीन तक.
Moon is between earth and sun, yeah, so you can't see the sun. Sun is, you're seeing a shadow of the moon on the sun. Yeah, moon is not very big, but it's closer to us, so it can cover the whole sun. वैसे तो नहीं cover कर सकता, लेकिन because it's much closer, तो वो view block हो जाता है. Yeah, but we can predict solar eclipses, you know, because we have the exact formulas. We can predict them. So that's a deterministic event. Earthquake.
लेटर
At this moment or till now, random, right? We पता ही नहीं चलता. We know what is happening. The plates are scratching against each other or shifting a bit, but when exactly will they shift? Somebody said, okay, let's put sensors in every bit of that. Even then it will be too hard because there's so many forces and so many factors involved. This comes in the category of maybe it's not really random, but for all practical purposes it is random because it's just too hard to calculate all of that.
वेदर फोरकास्टिंग
What do you think? Random or deterministic?
मैंने जितना पढ़ा कुछ
Weather forecasting is deterministic? No, no, it is random. There is like possibility that it will be wrong. Sometimes they miss some events. Sometimes they are off by large margin.
मैंने जो पढ़ा था वेदर फोरकास्टिंग इज वेरी क्लोज टू स्टोकेस्टिक बट इट्स deterministic model because
I
it's
think
highly sensitive dependence on the initial condition. If there is slightly change on the initial conditions, then it will not.
yeah, you are going. Weather is actually again as we discussed the chaotic thing.
Yeah.
So a lot of these random things that we say, as I said, many of the things that we will call random here, if you say I'm going to put sensors in everything and know from the very beginning their initial conditions and how each atom or each particle moved from there on exactly, then yeah, it's not random anymore. Yeah, so in that sense it is, but it's very hard to um, model the weather or know all those initial conditions. So the current models that are being used are basically stochastic models. Okay, some people bring in some sort of chaos theory, chaotic models in there, and in that sense again it's it's more of a philosophical thought, yeah. But for practical purposes, that is still random. Okay. Otherwise, people will tell you exactly what's going to happen in the next hour or 2 hours or 3 hours.
And there
Right?
was a philosophy कि अगर जो तितली है वो अगर पंख हिलाएगी तो तूफान आ जाएगा फ्लोरिडा में. That's kind of
Yeah, yeah, that is the butterfly effect, and that is the popular description of chaos theory.
chaos
तो
theory.
वो आप पढ़ें थोड़ा सा, what is the chaos theory, how it was discovered. It's a very good thing. It's being used nowadays. Chaotic control theory also people use chaotic models to try to control behavior of systems. It has applications. It's fair to say they are relatively limited compared to
Right.
the general stochastic or the
So we can say that
deterministic methods.
chaotic theory हम हमारे पास जो है हमारी randomness को मॉडल करने के लिए काम आती है, हमारी randomness को restrict करने के लिए.
You could say that, but the problem with that is when you go with chaotic models, you are pinning your hopes on knowing or guessing the initial conditions and then working with them, right? If you are going to guess different initial conditions, if you are going to guess or say randomly assign them maybe, then you're going back to stochastic models, right? So there is a mixture, and as I said, the difference mainly is that chaotic processes appear to be random, but they are actually fully deterministic. The only thing is we don't know the initial conditions, yeah, or we may be missing some parameters in the model because of which it seems a bit random. So yeah, you can look at that in chaotic models. Is interesting to see, right? So we just mentioned a few events, right? We saw the moon passing between Earth and Sun. We have the orbital motions. We know them. You can just put it in a computer and get when the next solar eclipse. We know, right? When the next solar eclipse is going to be. Then rolling a die and showing even number, random. Yeah. Okay. So next student coming in being taller than me, again random. Yeah. Next student coming in being from Swabi region, yes or no, is that person from Swabi or not? Again it is random. Yeah. And we have discussed that.
सर क्रिप्टो करेंसी की जो मार्केट हमारे पास होती है उसमें भी हमें कुछ मालूम नहीं होता कौन सा कौन कब कहाँ चला जाए, तो वो भी एक डिटरमिनिस्टिक.
Not just crypto, stock exchange is a highly random stochastic process. Actually we will see in this work, when we go to stationary processes, it's highly non-stationary also. Okay. And even there is something ergodicity, where it's also not very ergodic, so we will see that. So it's a very complicated stochastic process. So they can be easy, simple, so random processes. Stochastic and random both mean same thing. Yeah. Probabilistic basically. Okay. So what's a variable? We just discussed event, something happening. Yeah. The next person coming in is he or she from Swabi. Yes or no? Random thing. Yeah. Event. What's a variable? Not the random one. I mean, just a variable. अभी तक आप मैथ में तो काफ़ी यूज़ करते आ रहे हैं.
Variable is kind of our quantity. We assign some alphabets to that quantity. That is simple variable. If we have some like events, yeah, we can say some have model, then we assign some alphabets to that model or event. Then we
Assign
can
alphabets, so it's just a matter of going to alphabets. What if I was assigning boxes and triangles? Would it still be a variable?
Sir, I think variable is a portrait of numerical value.
Right. Placeholder.
Placeholder.
Box. Yeah. So I mean, without assigning alphabet, area of a circle I could write as pi triangle square. Yeah, I would say this. Yeah. Give them names. They are just what? Place holders. So if you now tell me that this triangle is 10, I can tell you what to put here, right? So a variable is basically what? A placeholder Why did we need placeholders? What happened going from 2 plus 2 equals 4 to this placeholder thing? क्या हो गया था दुनिया को? Why is it useful? Why is it needed? Placeholder.
Because it's a general way to discuss.
General relations from constant statements. 2 plus 2 is 4. Yes, okay, that is fine. But a plus 2, yeah, is, let's say, greater than a or something like that. Now you are able to give what? General relations, right? So then basically it's safe to say variable is a placeholder that gives relations or holds data in algebraic form. Yeah, so it's a placeholder basically. And you know, okay, a is pi r square. Right, so for example here, now you could say, okay, the area, if a circle has radius 1, what's the area? So if a circle has radius, let's say 2, then the area is, so you could say
4 pi.
4, you could say, okay, area and radius. So if the radius is 1, the area is pi. If the radius is 2, the area is 4 pi. If the radius is 3, the area is
9.
sorry 9 pi. Yeah, how inefficient is that? So much information. If we didn't have variables, pi to constant है ना, तो fixed value है उसकी, yeah. So I could write here 22/7, that's fine. But if we didn't have variables to assign relations and then hold the results of those relations, results भी उसके अंदर ही पड़े होते हैं ना. So how inefficient would that be? Yeah.
Reduce our space.
Yeah, it will be very inefficient and rather silly. And then solving it, it helps us then to the inverse relations. Now what is our, go for the square root thing. Yeah, here you will try to find patterns, but that is where the power of algebra, the variable, comes in. Yeah, so it's a placeholder, and it's also safe to say that it is something that helps us model the situation, isn't it? ये सारी values, all of these, you have just written a general model for that. What's the model? That is a square relation with the constant. What's the constant? Pi. Proportionality constant is pi. The relation is square. That is what you are saying. You didn't need, actually you don't need even a and r for that. You could just write it out. But the very idea of writing out in a general form is where the power of algebra comes in, because then you can start reversing things, apply other form. And of course it helps to put some symbols here that we can manage. Right, so deterministic, very good. Okay, is, what about if I say there is a variable x which is height of next person entering the room? Yeah, I like to mention this many times because same example, because it's easier to relate to for you. Yeah, is this a variable?
Yes.
Yes. Is it deterministic? No. Yeah, so it's still a variable. It is still going to hold some big range of information, right, depending on what really happens. Here also a doesn't have a value until you give me value of r. आप बताएंगे तो मैं ये बताऊंगा, otherwise a doesn't have a value. Similarly this thing doesn't have a value until this happens. Yeah, something happened. So x is a random variable. So events can be deterministic or random. Moon between earth and sun, deterministic, because we have formulas for the rotation, speeds, everything. Earthquake, for our all practical purposes, is random event. Variable can be deterministic or random. Now let's say, can we make this random? This was just giving you the fixed relation. The relation is not going to change. Okay, but can we make this, let's say the area of a circle, can we make that random?
By changing the value of r.
Changing the value of r. Okay, but then you put 10 here, it's 10 square, so 100 pi 8. Yeah. How exactly will you change the value of r? That can make a random. Let's say I say that I am going to pick the radius based on the results of a random event.
Okay.
Okay, then is a random now?
Yes.
हो गया ना random? You are already bringing in randomness. Yeah. So I say r will take a value depending on, you roll a die, whatever value you get, r will take that value. Yeah. So the way you assign this value,
Yeah.
if the way you do it is random, yeah, then this whole thing becomes a random thing. So let's write it to emphasize the randomness here. So far you haven't gone beyond this. You may have gone into a deterministic thing that radius is changing with time and the change is linear. You may have done formulas like that, and then you can of course see AT. I'm not talking about that one, yeah, which is also deterministic. You may say that r is linearly increasing with this slope. Then a is of course changing. Yeah, I'm talking about assigning r a value based on a random event. So I'm going to write it as r omega, just to emphasize that. Okay, later we will start skipping these things. This is the omega. It's, remember this thing? So there were omega 1, 2, 3. It can be one of those omegas. It could be a collection of them, like event A, event B. Yeah, but I'll just call it from here on just one omega. Omega is a random event. Let's say, as an example, let's say omega based on rolling a die. Okay, so if that is the case, then we know that okay, we are coming into what, randomness now. This omega is now for us is random, and not every random thing we can work with. Okay, randomness requires, the one we work with in probability theory requires that there is an associated sample space with it. अगर वो आप associate नहीं कर पा रहे for some reason, it's very hard to work mathematically. There is a probability measure associated with it. Remember we discussed axioms for this guy.
Yes.
Yeah, and then there is a sigma field. मैथ में fields पता है, algebras, what's a field, पढ़ा होगा आपने. Yes. So I won't go too much into detail of this. This is very intense probability theory stuff. You can read up, but basically it says that there is some algebra, set algebra, associated with omega that allows unions, intersections, etc. inside omega to be closed. Okay, it's a theoretical requirement for probability measures to be assigned. Okay, so we are saying omega is random, but not random like random. Okay, we don't know anything about it. There are conditions on it. There is a universal set associated with it. There are some set algebras that are closed inside omega. Okay, and there is a probability measure that we can assign to it, and we already have the axioms for that, how what it should allow. But after this we will mostly skip this bit. Okay, so we'll say okay, omega is random. Yeah, this is one example. It's not like omega is this thing. Yeah, just one example which you easily understand. Omega based on rolling a die. Now that is one interesting thing shows up from here. Let's say you roll a die and you pick R omega, then what values can A have? Firstly, what values can R have?
Depends on omega.
Yes. So let's say omega is based on rolling a die. You roll a die
Yeah.
and then you choose omega, right? So what's the value of omega?
1/6.
If it is equally lively, then omega equal to 1 over
No, I'm
6.
not assigning probabilities yet, right? I'm saying, okay, what values will omega take? Or
Omega
what
1, omega 2.
it can take 1, 2, 3, 4, 5, 6, or
Yes.
what else? So even based, the thing is here, this is the interesting bit here. Even after you base something like this on a random event, yeah, the mapping you do will decide how this formula looks. Okay, the mapping. Now what do I mean by mapping? Mapping means here, let's say I'll give you examples of 3 mappings. There can be actually infinite number of mappings. So I say mapping 1 omega. Look, I'm not saying omega is the number showing on the die, right? I'm saying omega is based on rolling a die. That means I can map it many ways. One way is to say omega is number on the die. Okay, so what numbers can be appearing on the die? 1, 2, 3, 4, 5, 6. So what values omega can take? 1, 2, 3, 4, 5, 6. So then, if that is the case, then I say, okay, there is still something left. I say R omega is omega. This is my one mapping. Okay. Based on this mapping together, now what are the possible values of R? I'm not asking for probabilities yet. Yeah. What are the possible values of R?
1, 2, 3, 4, 5, 6.
Yes. Why? Because now I locked what I mean by this. Yeah. Here based means general. I'll show you. It could be based in another way on the same event. Yeah, on the same experiment. But these two together will tell me what exactly mathematically I can put here. Now R omega can be 1, 2, 3, 4, 5, 6 depending on what shows here. Yeah, if it's 1, so let's do another mapping. Mapping 2. I'll just match what I wrote here. Yeah. Let's say I keep the first thing same, number on the die. So omega can be 1, 2, 3, 4, 5, 6. But then I say R omega is omega square. Okay. So going from random origins, random experiment or random events to the random variables is not unique. You will decide. Okay, your experiment, your needs, whatever, they will often decide. The mapping can be very different from one setup to another. But of course, you have to decide this at some point. Now, omega is number on the die. R omega is omega square. What are the possible values of the radius?
1, 4, 9, 16.
Yeah,
25,
squares of that.
Yes.
Yes, and then the possible values of A have now changed. Right? It is a random variable here. It is a random variable here, but possible values are
Different.
changing. Yeah. Okay. Another mapping. Maybe I want to do a third mapping.
There can be lots of possibilities.
Yeah. Infinite actually.
It is random.
So there, in random variables or in random events, we have random mappings.
No. Mapping is not random. There are many possibilities. You will decide which is suitable for your case.
We have
Right.
to fix this.
Yeah. For your situation. Yeah. Rolling a die is not really a real problem. Yeah. So this is just to give you an idea that from one uncertain event, you can get lots of different kind of ranges or possibilities depending on what mapping you are expecting. Usually it's the reality of the experiment that will dictate which one to use. Okay, here I want to give you the idea that okay, you say my omega is based on some random thing happening. but based on can be interpreted in many ways. You will have to decide it. You don't leave it open. Okay. So here I'm just emphasizing that there is some variation. Now I say okay, omega is number on the die, and I say A is omega such that omega is even, and B omega such that omega is odd, and then I say this is still basic mapping. Then I say R omega equals 0 if omega is in A, and it's 1 if omega is in B. So mappings can turn out to be complicated also. We won't make it complicated just on purpose. Fun के लिए नहीं करेंगे. But there will be situations where things will be like this. What's the height of the next one? Yeah, but let's say I do one thing if the next person coming in is taller than me, and I do another thing if that person is shorter than me. So I've decided same event, someone coming in, their height, but the way we react to that may vary depending on how we map the situation. So what are now the possible values of A? Firstly, what are the possible values of R?
0 and 1.
0 and 1. Even though the underlying random process, this guy has 6 possible values. You lump them, the evens in one direction, the odds in the other. What are the possible values of the area?
0.
0 and
0 and pi. Yes. So now we will not, every time we will not go into the full details from later. This is the first time, so I want to establish for you, I want you to see going from deterministic to random has this background. But in future we will just say R is random based on this distribution or this experiment. Okay, and this mapping. So actually we'll skip all of that. Usually we'll just go to distribution. We'll see that. R is uniformly distributed in this range. That's it. So but we have to get there. Yeah. So mathematically this is what's first happening, all of that. Now there is an interesting term here that we may need to come to, but we'll do that later. For now I'm going to define a random variable as a variable that takes a numerical value based on a random event. Okay, for us now, summary. It's a variable that takes a numeric value based on a random event. Okay, so I'll come to next why it needs to take a numeric value. Mathematics works with numbers. Yes, no के साथ काम नहीं करता हूँ. So we need to map somehow. So we will see that also. But here now the based part I wanted to emphasize could be infinite ways of doing it really. Yeah, you could map it like this and then change the relation. You could map it like that, whatever. But that's it. So now the random variable itself can be discrete or continuous. Okay, so you know what's a discrete set or discrete number? You know that, yeah, and you know continuous also. Okay, so in undergrads I also explained that, but you guys hopefully know that. So in these examples, is R omega a discrete random variable or a continuous random variable? On all these examples,
Discrete random variable.
it's discrete. Why? In each case, here it had 6 possible values.
Yes.
It had 6 possible values. They were different, but here it had only 2 possible values. In each case, they are discrete. Yeah. Okay. It can be continuous also. Can you give an example?
For example, let's say event that the height of an next person.
Exactly. So and assuming that we can measure to infinite accuracy, actual height would be a continuum, right? From
5.62 to
yeah, it will be a big range, but within that range it's a continuum. Any value is possible. Yes. So we will come back to this in greater detail. continuous random variables, discrete random variable. Then we will even go into continuous state, discrete state, random variable. We'll see that. Yeah. But here I'm just explaining or expanding on from variables now, random variable. Then just like your variables in real thing, they can be then continuous or discrete. But their way, their definition of continuous or discrete is based on the event thing, or basically the values they can take. Yeah.
How we could assign the value? That is.
Or what is the nature of the value? Like the height, we know it's a length is a continuous thing. Yeah. But let's say how many siblings does the next person coming in have? Now the nature of the problem itself is discrete. They can have one sibling, zero sibling, three siblings. बहन भाई कितने हैं उनके? 15 हो सकते हैं, 12 हो सकते हैं, लेकिन 15.3. So it's the nature of the thing that you are looking at. Okay, so to summarize, we have gone from random from base deterministic event to random event, deterministic variable to random variable. Now, what's the relation between random event and random variable? Okay, so a key relation between random event and random variable is that a random event can have non-numeric value. Okay. Here the random event was rolling a die and reading the number. That had a numeric value. Yeah, so it's also a random variable. But let's say the next person coming in is from Swabi region. Yes or no?
No.
That's a random event. Okay, yes or no, two possibilities. But that thing is not a random variable, because variables require numeric values. Okay, so if you are saying omega is equals is next person from Swabi, and the possible values are yes and no, then it is a random event, but it's not a random variable. To be a random variable, because we're going to work with mathematics, yeah, you need it to have numeric value. So what do we do in these situations?
We'll assign numeric.
You can assign numerical value.
0, 1.
Yes, or minus 1, 1. Again,
Yes,
this will not be unique.
Yes.
Okay, you will decide. So there's, but yes, what we can do is, if there is a random event that has non-numeric value, yes, no, you can assign it numeric values. So make this yes a 1 and this thing a 0, and now it becomes a random variable. And you can work in mathematics from here. Okay, random event is not necessarily non-numeric. Okay, random event can be numeric like here, and then it qualifies for the title of a random variable. The only difference, then what is the difference? Random event is something bigger. It can have numeric values, it can have non-numeric values, whereas a random variable must have numeric values. If it is based on some non-numeric random event, then you have to assign some mapping to it, and that will not be unique, by the way. Again, your experiment or needs will decide it. But once you have assigned or mappings, numeric assignments, then it becomes a random variable. So you can always convert a random event into random variable. That is fine. Now, one important term that we use in this field is realization. So now realization. एक तो realization होती है, आपको अचानक ख्याल आता है, yeah? That's the realization you have, yeah? But in our terms, in our work, it's this. Once the when the outcome is available, or the outcome of a random variable becomes fixed, yeah, when the outcome has happened, okay, the event has happened, and you know the outcome, okay, then the value the random variable takes becomes one realization of it. Let's say um, in this case, for example, at the start r is a random variable. Yes, it can take, in this case it can take what values, 1 2 3 4 5 6. Yeah, but now I tell you that okay, we roll the die and we got 5. So what's the value of r now? 5. What's the value of a?
25 pi.
25 pi. Yeah, so for r, that 5 we will call it one realization. Okay, that is, originally it was random, but now the value is known, it has become fixed, and this is one realization. Now in this case, if I wanted to draw the circle with this mapping coming from a random variable, what are the possible realizations of this circle? 6 possible realizations. Yes. And what are they? So each one of these is a realization. Radius 1. Yes. So by once you know the radius, a is a random variable, but the area is also now fixed. Yeah, pi basically. Then there is radius 2 for this mapping. Realizations will be different for different mappings. Yeah, but for this mapping there are 6. Okay, I don't have space to draw bigger, but you get the idea. It will be bigger and 1 2 3 4 5 and 6. Yeah, अब ये it becomes an oval, but no, it's still a circle. Yeah, I don't have space. So these are the 6 realizations. So we say, what are realizations then? Realizations are basically all the possible values or the shapes in this case. Yeah, all the possible values that the random variable can take. And when it takes one of them, we say okay, it has taken this realization now. But at the start your world was all of these. शुरू में तो आपको नहीं पता था ना, right? So once the outcome is available, the value of the random variable becomes fixed, and we call that one realization. So I will come back to this term when we go to random processes. It will become important.
Why it's so important that we know the values and we fix to random variables?
We have to know the values.
Why so important that we know the outcomes is there and we assign to values to the random variables?
Why do you think? Any idea from these circles? Anything? For this toy example, let's say you were going to make a circle, one of these circles, yeah, or with a piece of paper. Okay. Now, how much paper should you buy from? What size paper should you buy from the shop?
Big size paper.
कैसे पता चला? Biggest realization, right? What's the average size realization? Middle वाली कहीं आ गई. What's the smallest it can get? What's the if a self-driving car is driving and it sees picture of a cycle that's just this small, should it identify it as a cycle or just some toy on the side of the road or a picture? Yeah. So even when there are randomness, yeah, the realizations often will help you decide or make understand the range of possibilities.
Okay.
And then we don't just go for the maximum and minimum, then we will also work with what's average, what's the standard deviation. So realizations help us observe the universe of possibilities for that problem. For this particular problem, the universe of possibilities is this. अब आपने जो उस पे whatever, if this was, you were supposed to make say this cover of a manhole with concrete, yeah, and you knew okay it could be this or this, 4 possibilities. How do you plan it? Do you go for the maximum? Do you go for the average? How do you plan it? So these are toy examples, but in effect this is what expands to real situations. Okay, so knowing realizations or having an idea of the realizations can help you in designing, in decision making. As I said in the very first lecture, that is where we want to go. It's always about making some decisions, designing something. अगर वो ना करना हो तो मतलब probability theory can also be a theoretical curiosity, वो भी है. But this is applied maths, so there we want to be able to use it somewhere. The Brownian motion you get every time you put in the pollen grain, what motion it takes is fixed, right? वो तो fix होती है, but that is one realization. Next time you put it there, it will take another realization. Third time you put it there, it takes third realization. Then you try to find out what are these realizations of. What is the process? किसकी realizations हो सकती हैं ये सारी? Yeah. So there also realizations help you. As we will see in this course, they are actually realizations of a special Markovian process called random walk. Okay, and when we will actually write that formula and then try to get its realizations, they will look a lot like what this guy does, this Brownian motion in of the pollen grain. So realization is a term which we need to be familiar with, and of course it has implications for us that we will see. Right, so what's the time by the way? Yeah, I'll just mention the random process and then maybe we can finish for the day. So we'll go to assigning probabilities next time. Okay, we already talked about assigning probabilities in the sense of the rules of assigning, not really. Yeah, so we'll go further in some details, but last thing I want to mention for today is going from say random variable. So we went from event to random event, from random event to random variable, and we also linked variable to random variable. Now we can go from random variable to random process. Yes, so if you put a t here, changing with time, then in a way it's a process, things evolving over time or space or something. Yeah, but that was still deterministic mostly. In our case, we want to now go from random variable to random process. Okay, what can that be? Let's see. Let's say I say that x is the height of next student entering, next person entering. X is what now? A random variable. Okay, good. But what if I say that I want to record the heights of next 5 students, 5 persons coming in the room one by one? Yeah, let's say they are coming in one by one, and I want their heights. Okay, so now what is this? It's a collection of random variables, right? Now it's not just one variable, the height of the first person coming in, the height of the second coming in, third coming in, fourth, fifth. Now this is a collection of random variables, yeah, and together they form a random process. Okay, this is a special random process in the sense that it is collection of discrete events. We will see that later, but for now I want to mention this. So height of first person coming in, second, third, fourth, fifth. Yeah. Okay. So here, is it continuous or discrete? It's a height. Yeah. So the height, yeah, it's continuous. Yeah. So let's say in the first lecture, first person who comes in has this height, second person who comes in has this height, third person who comes in has this height, fourth, fifth has this height in the first lecture. Yeah, so together I can say they form one realization of this random process for this lecture. Now in the next lecture, next time we meet, the first person coming in has this height, second coming in has this height, fourth coming in has this height, sorry, third, then fourth has this height, and fifth has this much height. Then this is the realization in the second lecture.
Second time it means.
Yeah,
T1,
in
T2.
in some sense. So for us, it's, we are distinguishing by lectures. So in the first lecture, the random process had this realization. In the second, it's the same random process. Process the same, but realizations are varying. Yeah, and these realizations are bounded in some way. Remember, human heights cannot be negative. Nobody has, no human history has anybody taller than, let's put in extreme case 20 feet, right? So we know all these realizations have to dance around inside this range. Yeah, but now we have gone from a single random variable to a collection of random variables, and we will call this a random process. Yeah, this is one example, but in general, this is important to understand. A random process, we can write like this, where t is in some big set T. There are two distinctions. The value it takes can be continuous or discrete, like the height case is continuous. Yeah. What if I was not measuring the heights? I was saying, okay, how many mobiles the next 5 people coming in have? Okay. So how many mobiles can they have? 1, 0 to आजकल नहीं होता. It has 0, 1, 2, 3. Yeah. So then these values on this, it's discrete here already, but here also they will become discrete. Yeah. But in general, this y-axis thing, if that is discrete or continuous, so it can be discrete. Later we will call this discrete state random value. The states it can take are discrete, yeah, or continuous.
So we will fix omega for that.
Hang on, let me just write this one. Here also it can be discrete versus continuous, and this one is here. Okay, the x-axis thing. Okay, now what's the question?
The question was that we will fix omega on that process. If our omega will change, then our random process will also change.
Yeah. So I'm saying you have already decided whatever your omega is, what event it's based on, what's the mapping. Yeah, you will have to decide that. It will depend on that. But
now we have add another dimensions that t.
Yeah. We have included now one more dimension. Yeah. What if you take away t? Then you're talking about some deterministic thing. Yeah. The omega, the person coming in, that is the random thing. Yeah. Uska yahan hona zaruri hai. But in most of this course, we will start dropping this. We will either talk about x and we'll just say it's a random variable, or we will say it's a random process. Okay. We will start dropping this by simply saying it is random in the statement. That's it. So you will not always be bothered by this. For now, I just want to show you that it is there. Have the module. But now, at the moment, I'm not giving it any values. All I'm saying is I'm deciding its major classes. It can be discrete or continuous in the value it finally takes, and it can be discrete and continuous in the steps it takes between different values. Yeah, so it can be continuous or discrete here. Yeah. So we will see examples of all 4 of these next time, or yeah, we will see that. So any questions in that? No. So can you think of what would make this continuous? The example I gave, I showed you in both cases this was discrete. One case this was continuous, like height and number of mobiles, this was discrete. What about this guy? Can you make it continuous? What can you imagine? Change the experiment, of course. people coming in will be discrete mostly. Yeah. So what it could be something else, the temperature in a room changing over time. Yeah. Then the this thing, the time, the real time thing, the time that we measure, it's in reality it is continuous. Yes. Although I think in a pure philosophical sense, from relativity theory and stuff, I think even time is discrete. वो Planck distance है ना, smallest distance possible. So the light can, the amount of time it will take the light to cover that should be the smallest time possible, something like that. I think, but but for our practical purposes, time is a continuous random, continuous variable. Right. So we will see some examples of those also. To quickly summarize, what did we do? We went from deterministic to random. Yes, in event, in variable, and in process. Right. So next time we will go further. Now we will continue with this guy. Okay, and we'll see. Okay, what are the different classes of this X? Finite, countably infinite, uncountably infinite. कुछ याद है?
Yes.
पता है? ठीक है. We will try to see for each case what happens. Okay. So I guess that's it for now.